What do the experiments say? G equals 2.00 for an electron. That means since G is positive and Q is negative for an electron, the magnetic moment and the intrinsic spin angular momentum are in opposite directions for the electron, always. 5.58 for a proton. And Townsend says that G is minus 3.82 for a neutron. So this means that even though the neutron has no charge, it still has a magnetic dipole moment. But something's fishy with that formula, because for the neutron, Q is equal to 0. So how can that possibly yield a useful result in this equation if we substitute Q equals 0? Well, it turns out that what Townsend meant when he said that G is minus 3.82 for the neutron is that the magnetic moment equals minus 3.82 times the charge on the proton divided by 2 times the mass of the proton times the speed of light times the spin angular momentum. By the way, we define for convenience a quantity called the Bohr magneton. It's kind of a unit of magnetic dipole moment. Mu sub Bohr equals E h bar over 2 mass of the electron speed of light, which happens to have the value of 5.79 times 10 to the minus 9 electron volts per Gauss. And the nuclear magneton mu sub n, which is E h bar over 2 times the mass of the proton times the speed of light, which is a lot smaller. It's a convenient unit for dealing with magnetic moments of protons and neutrons and nuclei. So the magnetic dipole moment of particles tends to be inversely proportional to their mass. So electrons have larger magnetic moments than protons and neutrons. So let me tell you a story that was told by a man named Victor Weisskopf, who was a big shot in the old days, the glory days of quantum mechanics. He says, there was a seminar held by the theoretical group in Göttingen, which is in Germany, and we had a visit of Otto Stern, who was in Hamburg, not very far. Otto Stern of Stern-Gerlach fame. Stern came down to Göttingen and gave a talk on measurements he was about to finish of the magnetic moment of the proton. He explained his apparatus, but he did not tell us the result. He took a piece of paper and went to each of us saying, "What is your prediction of the magnetic moment of the proton?" And every one of them, from Max Born to Victor Weisskopf, all said, well, of course, the great thing about the Dirac equation is that it predicts a magnetic moment of 1 Bohr magneton for a particle of spin 1/2. Then he asked us to write the predictions down. Everyone wrote down 1 magneton. Then 2 months later, he came to give again a talk about the finished experiment, which showed that the value was 2.8. He projected the paper with our signatures on the screen. It was rather disagreeable. So the 2.8 he's talking about is related to the G factor of 5.6 that we talked about a second ago, 5.58 for the proton, because there's a slight difference in the definitions of the numbers we're talking about, a factor of 2.